doesn't want to go away.
Oh, this over here.
Oh, yes.
So looks like we can't see the top or quite to the right bar.
Okay, let's see.
Oh my. That's menus.
Oh.
Using an introduction, probably no. Following me, but it's still down with the light.
Okay, you're gonna push it up now. Is it focused or not yet?
It's focused.
No.
Maybe up just a little bit more.
I'm sure more of the forward. Oh no, that's too much. Yeah, that's good enough.
I think that's good right there.
Let me just fix it.
Yeah, that's fine. You can see the middle part of the board, not the left and the right, but that's fine.
See, hopefully it's not following me. Good.
It's following me.
Is it? Stupid. Okay.
You need to zoom out a little bit.
Zoom out.
It zooms
Yeah.
back.
So you want to see more or less?
Back down.
Less down.
Open the menu again.
Is it clear or not?
Still up a little bit more.
So you want to see.
Okay, then zoom out a little bit.
Fix it first so it doesn't follow me.
It is not following.
Good. Is it clear, guys, or still not?
They can't quite see all the way to the right side of that equation. There we go.
Still blurry or is it clear enough?
It's clear.
Okay, good. That's the best I can do, guys. Let's see. Okay, I think we started last time. We stopped in this problem. And I think we found so we started with this problem and we said, let me just here.
And we didn't quite have enough time to find all the coefficients, but we had solved everything else.
So we said, when we factor out the denominator, if we end up with complex like these, characteristic roots, don't factor these anything beyond s squared. Keep it as it is. So this one will be factored than K1 over S, which is these, and then S squared plus 10S is here. In the numerator, you have to have S 1 unit less than S in the denominator. And then the power of S in the denominator, S squared, then you have to have here at least S. If you have here S cubed, then you have to have here S squared, such that when you add these, you can have all possible values. Now the question is, how do we find a S and B? And we did through, and we found A and B to be minus 6S minus 54. So now the question is, how do I find the inverse Laplace transform of this one? Well, this one is easy. 1 over S is just U of t, multiplied by 6. But what about this one? What's the inverse Laplace transform? I can use the table. In the table, I have this one. So this looks like this, with big A, if I compare it to that one, is minus 6. Big B is minus 54. Little a, here is 10 equal to a. So little a has to be 5, 10 over 2, and C equal 34. Now I need to find R. A, I have it. Little a is 5. I need to find B, and I need to find theta, and I'm done. And if you go back to the table here, this table here, that is the value of R. This is theta, this is B. So I'm gonna plug just the value for R or B. B is easy. Then you can do for R and theta. So if I plug the value, to find B, it will be B equal square root C minus A squared. That is square root. C is 34 minus A is 5, so square is 25. That is 9. That is 3. So we found this, B, which is 3. And same thing, you're going to be using these equations. You have all the parameter here. So you can find R and you can find theta. And your final answer will be, if you do that, and I went through this in the video in detail. The final answer will be, this is R, 10. This is, we already found this is 3B, and this is theta. And that's the answer. So if you have this Laplace transform, then that's the inverse Laplace transform, x of t. The last one is when you have repeated root, like this one. Now, when you have this one, don't make this mistake. Like you say, okay, this looks like h of s, 8s plus 10 over s plus 1, s plus 2 squared. And you think all of this, I can break it out as k1 over s plus 1 plus k2 over s plus 2 squared. If you do this, then when you try to add this, you can find k1, and when you try to add this value, these two terms, you will end up, because this is s squared, you will end up with s squared in the numerator, and you will not be able to cancel it. So whenever you have these repeated roots, then you have to break it even to find the lower power. So that will be plus k3 over s plus 2. Now you can find the value of k1, k2, k3, and when you sum these three terms, you will get this term. If you ignore this one, when you sum these two, finding k1, k2, you won't be able to get this one. You will try it, and you will get equations that doesn't meet each other. They don't, like you're going to get two equations, k1 and k2, but you cannot solve them. Okay, now the question is, how do we find K1? How do we find K2? How do we find K3? There are different ways. One way to find K1, I will multiply every term here by its denominator, s plus 1, and multiply here by s plus 1, and set s2 equal minus 1. If you do this one, when you multiply this by s plus 1, you set s minus 1, that will go to 0. Same thing, 0. This will survive. And that will be K1. How about here? 8s plus 10 multiplied by s plus 1 divided by s plus 1, s plus 2 squared. And you said s equal minus 1. So only this will survive. The remaining parameters will disappear. This will cancel here. So this will never go to 0. Then you have here 8 times minus 1 plus 10 divided by minus 1 plus 2 squared. And here you will have 2. And now which one do I find? K2 or K3? Find K2. See, these two denominators the same. When you set s equal minus 2, they both will go to 0. So in this case, I find K2 that has the denominator to the higher power. Why? Because then I will multiply by s plus 2 squared. Then this will never go to 0, but this will go to 0. So to find K2, always start with the unknown that has denominator to the highest power. If you have the denominator equal, multiply by s plus 2 squared and then set s equal minus 2. When I multiply this side by s plus 2 squared, that will cancel here, and that will end up just with 8s plus 10 over s plus 1, and then you set s equal minus 2. When you multiply this by s plus 2, and you set s minus 2, that will go to 0. S plus 2 squared. When you multiply this by s plus 2 squared, this will cancel, and you will have only K2. And when you multiply this by s plus 2 squared, this will cancel only one of them. Then you set s minus 2, this will go to 0. And from here, you will have K2 equal, plug for s minus 2. This looks like 885. This is s. So minus 2 times 8 is minus 16 plus 10. Minus 2 plus 1 is minus 1, so that is 6. All right, so we found K2, we found K1. Now, how do we find K3? Very simple. Now, K3, you set any value for S, and you solve for K3. Because in this equation, you have already K1, you have already K2. The only left is K3, one unknown. So plug any value for S, that will make your life easy and will not make the denominator 0. For example, I cannot plug for S minus 1 or minus 2, that's bad. But I can plug for S0. So to find K3, set S equals 0 and solve the equation. So then that will be 0. Here, plug for S0, that will be 0 plus 10 over 0 plus 1, 0 plus 2 squared, K1, 0 plus 1, that's 1, K2, 0 plus 2 squared, that's 4. This is just S plus 2, the original. 0, that will be K3 over 2. And I will multiply everything by 4 just to get rid of the denominator. This is 4, so this will be just 10. Multiply everything by 4. So that would be 10. 4. K1, I already found it to be 2. K2, we find K2. Yeah, 6. Multiplied by 4 would cancel this 4 plus Multiply this by 4, you get 2K3. And from here, K3 will be 4 times 2 is 8 plus 6, 16 minus 10 minus 6 over 2 minus 3. So that's it. So we found now.
That should be minus 4.
Which one?
This one, not minus 6 over 2, it's minus 4 over 2.
Okay, let's see. 8 plus 6, 14. Oh, minus 4, thank you. And then this will be minus 2. Okay, so we started with this problem. We did partial fraction expansion, and we found K1 to be 2. We found K2 to be 6, and we found K3 to be minus 2. Now, the inverse Laplace transform of this one, I can use the table, h of t, which is this one, which is also the same here. And from the table, we have 1 over s minus lambda. It is it 1 plus lambda? Some textbook put plus and then this is minus, some minus, this is plus. So which one is in our textbook here? They have these. They pass the table.
Yeah.
Oh, here. So in the table, it's the minus and the plus. And this is minus and this is plus.
If you're writing on the board on the right, we can't see it.
I'm not seeing this one, yeah. So in the table, we have lambda t, u of t. It's 1 over s minus lambda. So we're going to use this property. So then this one, let me write it here. A lambda t u of t is 1 over s minus lambda. Okay? So this one will be 2. Lambda is minus 1. T u of t. Plus. How about this one? Again, we have in the table this one. Let me write it, show it here. We have in the table this. Where is it? Here. So we're going to use this one. So this will be plus 6t e. Lambda is minus 2t u of t. Plus the last term, minus 2 times plus, that's minus 2. T minus, lambda is minus 2. T u of t. And that's the answer. So in this inverse Laplace transform, we've covered 4 cases. The 4 cases are, first one is a simple distinct root, and in the denominator s to the power higher than the numerator. The second one is distinct roots, but in the numerator and the denominator s, same power. So you do that long division. The third possibility, when you factor out, you get a characteristic root that is complex, so don't factor it and just use the table this way. And the last possibility is we have repeated roots or lambda, s plus 2 squared. Then you have to factor all lower power, 2 and 1. And then you do partial fraction expansion. Okay, guys, I did you see the attendance? So if you, it is in the chat room, not in the chat, in the main channel. Let's see how many people. how do I get this one? Okay, this one. So only 23 students voted. Check the attendance. So if you came late, make sure to check these attendance, guys. Okay.
Us in person don't need to do that, correct?
Huh?
Us in person don't need to.
That's a good question. How do I know? Should I pass a paper?
Because I'm supposed to be online technically, so.
Yeah, if you are online, you can. Can you log in?
I have it on
with
my
your
phone. Yeah, I can do it on my phone.
Yeah, if you can, but if it's inconvenience for you, I don't want to punish you for coming. I'm actually appreciating you coming. So what we can do is just should I pass a piece of paper and just if you cannot sign on the phone, who cannot sign on the phone? Just write your last name and pass it to everyone. Right. Okay, let's see. So, all right, so the next topic will be property of the Laplace transform. And property of the Laplace transform we will use it to help us analyze a signal, analyze a system, and make our life easier. So the first one is linearity. What do we mean by linearity? So just imagine this is the definition of the Laplace transform. So just imagine it's a system that transforms the signal x of t from the time domain to x of s, the Laplace domain, or this is the frequency domain. So that's basically what's the Laplace transform. And we say x of t, this arrow, take it to x of s. And this arrow, you can do the inverse Laplace transform. So now let's assume we have a signal, and let's call it x1 of t. So we do the Laplace transform, we get x1 of s. Now what happens if I amplify this signal by a? A is a constant, maybe 3. You amplify the signal by a factor of 3. What will happen to its frequency domain? Again, x1 of s will be amplified by the same value. That's one condition for linearity. All right, let's create a second signal, and let's call it x2 of s. And let's say the Laplace transform of it is x2 of s. Now, if I have a signal which is a combination of these x1 of t and x2 of t, so this is a new signal that consists of both amplified by or attenuated by different constant. Then the Laplace transform of this one will be just the Laplace transform of this, which is this one, plus the Laplace transform of this one, which is this one. If this is met, then we say this, that Laplace transform is a linear operation. And that's what we have been doing. If you saw Laplace transform the inverse, we break a signal using partial fraction expansion to 3 different parts. Then we say the inverse of this is the same as the inverse of this plus the inverse of this plus the inverse. We use actually the linearity property. And that will give us the correct answer. And we will see how we're going to use it in next example. So let's move on to a new property, which is the shifting property, time shifting property. Now, time shifting property, if you have a signal in the time domain x of t, and that is the Laplace transform x of s, what happens if you shift the signal? That means you delay it by t0. T0 could be 5 milliseconds, 10 milliseconds. How is this going to affect the spectrum, the frequency, or the Laplace domain of x of t? You will get exactly the same, which is x of s, same spectrum, except now you're going to have a phase shift. And that phase shift is by minus T0. So minus T0, a delay in the time domain. It is a phase shift in the frequency domain. And there is some analogy to this one. If you say x of cosine omega 0t, that's x of t. Now, if I delay it, that means whatever you see t, you replace it by t minus t0. So that will be t minus t0. This is just equal cosine omega 0t minus omega 0t0. Now, when I compare these, and I think of it in the frequency here is still the same. So how did this delay impact this signal? It phase shift. This we always call it the phase shift of the signal. So phase shift in the frequency domain, when you think of it, in the time domain, is just delay. And that's what this E minus T0. Basically, it is phase shifted by T0. Now, here we are assuming x of t exists for negative t and positive t, and you move it all. But what if the signal is causal? That means the signal looks like this, something like this. And let's say it's u of t. That means it exists only for t 0 and positive t's. Now, if I delay these, now I have to be careful. It's x of t minus t0, u of t minus t0. And the time delay of this one will be just x of s, which is the Laplace of x of t, e minus t0s, which is the same as here. Same as here. If I delay all of them, then I get this one. But what do you think if you do this one, x of t minus t0, u of t? Now, these two are different. These two are different. So you cannot just assume this is x of s e minus t0s. That's not correct. That's wrong. Why? If you plot these, it will look like this. So that was x of t. This will be x of t minus t0, u of t minus t0. If I plot these, the original function was like this. Now, I shifted this x of t minus t0, so that will be this here instead of 0, it will be t0. Then the u of t here mean these. So what signal you will get? You will get that portion. You will end up with a signal that looks like this. T0. Because u of t start from t0. So it will count this. But here u of t start at t0. So it starts here. So anything here will be deleted. But in this case, no, this starts here. So that means this will be counted. So the signal looks different. So this is the correct answer. Make sure, and we will see the next example, that x of t minus 2 with u of t minus 2 delayed. To get the answer.
What would the bottom one equal?
Which one?
Yeah, what would that equal?
Oh, this, then you have to carry out the integral. You won't have it in the table, you just have to take the Laplace integral. And when you integrate, this will be from 0 to infinity. And then you will get, it's easy to integrate, it's not big deal. But it's not, you cannot just use the table. Let's look at this example. Here we're going to use linearity and time delay property. So we have this signal, and we need to find the Laplace transform. Well, we can carry out the integral and find the Laplace transform, and these signals are not really that difficult. Or I can break this signal to two simple signals. One that looks like this, which is this portion, plus this portion, which is this. So now x of t equal x1 of t plus x2 of t. And then find the Laplace transform of this one, find the Laplace transform of this one. I add them up, I will get the Laplace transform of this one. So I'm using here linearity. So let's start. So we're going to break this one to this. 1, 2, 1. Plus this pulse. And we call this x1 of t, and we call this x2 of t. Now, how do I express this signal? X of t equal x1 of t plus x2 of t. Well, let's find the equation of this line. It's a line, so that's t. The slope is 1 height divided by width, divided by 1, so the slope is just 1. And this line is shifted 1 unit to the right. So that would be t minus 1. And if you are not sure, plug for t2, 2 minus 1 is 1, which is this. Plug for t1 should be 0, 1 minus 1, 0. So that's the equation. And it only exists from 1 to 2. So that will be t minus 1, that's x1 of t. Now it exists between 1 and 2. It doesn't exist before 1, it doesn't exist after 2. So I have to multiply by a pulse. So that pulse will be u of t minus 1 minus u of t minus 2. That's u of t minus 1. This is u of t minus 2. If I add them up, I will get only that pulse. Plus x2 of t is 1. That's again, amplitude is 1. So that is u of t minus 2. So you get this, and subtract from it another one. Start at t4, u of t minus 2. This is x2. This is x1. So I can multiply this time this, minus this time this, plus minus okay. Here I have no problem because I can think of this as a signal x of t and this is u of t. And both of them are shifted 1 unit. So I can go back to the table. And I will use this property. T u of t is 1 over s squared. So I'm going to use this property. T u of t is 1 over s squared.
I can't see that at the top.
Huh?
I can't see the top that you're writing right there. I can't see that. Thank you.
Okay, it's working. Good. All right. So I'm going to use this one, but then I'm going to use also the time shifting property. T minus 1, u of t minus 1 will be the Laplace transform of this one, which is 1 over s squared. But then the shift by 1 unit is e minus s minus t0, that's t0. S. So I'm using also this shifting property. I'm using this shift property. Okay. So that will be easy. And this one is easy. That's u of t. U is 1 over s shifted. U is 1 over s shifted. Here is the problem. Why? Because this is t minus 1 shifted by 1 unit. So if x of t is shifted by 1 unit. The u of t is shifted by 2 units. They have to be, if I'm going to use this property here, both has to be shifted by the same amount. So we can use a trick, which is, if I make this t minus 2, then it will be multiplied by u of t minus 2, and both of them are shifted by 2 units. So how do I make these t minus 2? Let me put this one down here. Well, I can add minus 1, so that will be minus 2. But if I add minus 1, I have to add plus 1 to cancel it. Otherwise, I change the equation. So I can say, oh, this is just t minus 1. Minus 1 is minus 2 plus 1. This is still the same as this one, still the same. Time u of t minus 2. Minus 2 plus 1 is just minus 1. Okay, plus u of t minus 2 minus u of t minus 4. Now I can take these and multiply it by this one, and I will get both of them shifted by the same amount. Take these and multiply it by this one, and I get another signal, which is okay. So now this one will be x of t equal t minus 1 u of t minus 1 minus t minus 2 u of t minus 2 minus 1 time u of t minus 2 plus u of t minus 2 minus u of t minus 4. This will cancel. And this, I will use the table here and the time shift property. So the Laplace transform of this one now will be, the Laplace transform of t, u of t is 1 over s squared from the table. And it is shifted by 1 unit, and I just multiplied by the phase shift. E minus t0, so that's minus 1s. Minus. Again, this is tu of t, but shifted 2 units. So the Laplace transform of 2 tu of t is just 1 over s squared. And shifted 2, that's phase shift, minus 2s. And this is minus u of t in the table is just 1 over s. So that's 1 over s, shifted 4 units. So that's e minus 4s. And that's the answer. Here, this example just to demonstrate how you can use property to simplify the solution. For this example, actually, it's easy. If you carry out the integration, probably same number of steps. But there are scenarios where you get a function, really, you cannot find the Laplace unless if you break it down to simpler circuit, then use linearity and property. Okay, let's see. Frequency shifting. And this frequency shifting, there is a big application for it. So in communication, if you have a signal x of t, the time domain, and the Laplace transform, we say this x of s. Now, if I multiply the signal by es0t, now es0t, S0 is just sigma plus j omega. So that's the same as E sigma 0 plus j omega 0. That's what S is, sigma plus j omega t. If I imagine sigma is just 0, I can choose sigma 0, no decay. This is just E j omega 0 t. Now that is cosine plus j sine. That's a sinusoidal signal. So these, you can think of it as a pure sinusoidal signal. So that's modulation. We later chapter, when we come to the frequency response, we call this modulation. But if you multiply a signal by es0t, then the spectrum will change. How is it changing? It will be x of s minus s0. That means the whole spectrum here, instead of centered around s equals 0, now it will be centered around s0. So by modulation or multiplying the signal in the time domain by this exponential, that means you are shifting the frequency from 0 to be centered around S0. For example, let's say you have this simple pulse, x of t. If I do the Laplace transform, I get this sinc surface. So that would be x of s. Now, if I multiply this signal x of t by this amount, by this signal, which could be just pure sinusoidal with, it's like, it could be just pure sinusoidal like this, depend on sigma plus j omega 0. Or it could be some, oh, they cannot see. Oh yeah, here. Here's sigma 0, it's this one. So it can be as simple as sinusoidal like this. That means I multiply the signal by this frequency. And if sigma is not 0, it will be something maybe like this. So if I multiply a signal by this sinusoidal, it's modulation. What is the impact? I am shifting the spectrum of the signal to be centered around S0. That means centered around here instead of centered around here. So by multiplying this by es0t, the whole spectrum here will be shifted. Instead of centered around 0, this is sigma, this is j omega, which is s. Now it will be centered around s0. And this is sigma 0. Here it could be -3, and omega 0 here it could be 1,000 hertz. Now, why do we need to shift the spectrum? I said one of the applications is in communication. Imagine two people, like in your neighborhood, there is 150 houses, and everyone is talking the internet or in the phone, and different conversation, different sound, and you want to transmit this signal in the coaxial cable or fiber optic cable. If you add them up and then transmit them 120 houses, there is no way at the receiver you can separate them in the time domain. No way. They will add up, you cannot separate. But if I do, before I add them up and send them the coaxial cable, I modulate this or multiply by es0t and multiply here s0 could be sigma 0 plus j 1000. Actually, they use like 1 million. And this I multiplied by S0, 0 plus J, 2 mega. So now the spectrum of this speaker will be somewhere like here. That's the spectrum. 10 mega. The spectrum of this one will be 2. So that it will be somewhere here. And now this spectrum, even though in the time domain they are added up and you won't even make sense of it, but in the spectrum domain they are separated. So then you send them up. At the receiver, they use filter. They filter out these, and then they hear John speaking. They take this to another band filter, and now they hear Samantha speaking without interference. And that is one of the big applications of frequency shifting. So you multiply the signal by ES0T, you just shift the spectrum to be centered around here. Okay. And also we do shifting. If I transmit a signal using electromagnetic wave for human voice, I need an antenna probably 10 kilometers to be able to transmit it. So we do this modulation or frequency shifting to a very high frequency, like gigahertz. Now I need an antenna like in your cellular phone, you don't even see it. It's like micro or millimeters down there to transmit your speech electromagnetic wave. How do they do this? They do this frequency shifting. Okay, let's see. I don't think I have time to do this, to start this. This is very simple. We're going to continue, but it's already in the video. I encourage you to watch it, but I will go through it next class. I should finish next class Friday over property. Okay, if you can really just make sure, guys, you check the attendance sheet that I sent in the main chat room for the course. Any question, guys? Yeah, raise your voice, please. Yeah, go ahead. Yeah, that's the same. Yeah, we call it carrier. This we call it the carrier frequency. S0, and S0 is the carrier frequency, yes. Good. Any other question, guys?
Is the quiz on Friday? We're having a quiz on Friday, right?
What did I send the email? Friday. Friday, yes. You're going to have 2 problems. You should really be solid Friday. Simple signal, use the integral Laplace transform to find it. Another, use partial fraction to find the inverse. You watch the video or what I explained today, you should be ready for it. And the homework problem. So it could be a problem from the homework. Maybe I'm going to change 2 to 3 or something like that. Similar to the homework.
Oh, you know
It was something.
I just like
I will be in my office
Yeah,
now.
we're gonna offer
If you have a question about homework, guys.